Question 125 is asking you to predict the geometry for the central atom in a few of these compounds. So what shape do these molecules have? And the shapes of molecules are important for the same reason that the shapes in the ridge of a key is important. It determines whether the key will fit into a lock or a keyhole and turn an engine on. And in the same way, if molecules have the right shape, they'll fit into a receptor site and turn a biological reaction on or off. And so the shapes you would want to be familiar with are these 5 here. We'll go through these one at a time. Just as a rule of thumb, and this has plenty of exceptions, but as a rule of thumb, carbon tends to form these top 3 shapes. Nitrogen tends to form this 4th shape, and oxygen tends to form that bottom shape. There are times when carbon, nitrogen, and oxygen don't form those shapes, and there are certainly other atoms that form those shapes, but that you'll find as a trend, those shapes tend to be associated with those atoms. So if you have the shape of a molecule is created by the repulsion between electrons. Atoms have electrons flying around them. All those electrons have a negative charge, and like charges repel. So atoms repel each other, they push against each other, and any atoms bonded to a central atom will try to get as far apart from each other as possible. For the same reason, lone pairs, electrons that are not in a bond, but are just around an atom, push against atoms, because the lone pairs have a negative charge, and on the outside of atoms you have electrons with a negative charge. So all these things are trying to get away from each other with the central atom. And when they get the furthest they can, the molecule gets its shape. So for example, if you have a central atom and there are 4 atoms bonded to it and 0 lone pairs, and actually, let me do this. If you have 4 atoms and 0 lone pairs, you can see that would look something a little bit like this. So here's our purple central atom, and we're going to put 4 atoms bonded next to it. And you can see the shape that it gets when all of these atoms repel each other. If you try to bring these atoms closer together, the electrons in their shells push them apart, and they get as far apart as they can, and you get this tetrahedral shape. So that is our first shape here. If, on the other hand, instead of 4 atoms, you have 3 atoms bonded to a central atom and no lone pairs, then you get a shape called Trigonal Planar. So here's our central atom. I'm going to add 1, 2, 3 other atoms, and there are no lone pairs here. And you can see that this sort of looks like a triangle. You can see how there's a triangle being formed there from one side, so trigonal. And if you look at it from the side, it looks completely flat. So it's all in a plane. So it's Trigonal Planar would be the name for that shape. And so when you have 3 atoms and 0 lone pairs around a central atom, you get that Trigonal Planar shape. If you have 2 atoms and 0 lone pairs, then the shape you get when they repel each other is linear. So it's just in a straight line. And they get that shape because these atoms are repelling each other, so if you force them close to each other, the electrons in them will push against each other until they form that linear shape again. Another one is if you have 3 atoms pushing against each other and 1 lone pair, you get this shape called Trigonal Pyramidal. Nitrogen tends to form that shape. So that would look like, so we have 3 atoms, so here's 1, 2, 3 pushing against each other, and 1 lone pair. So there we have 1 lone pair, and you can see that this, if you look at it from the side, let me arrange it here, if you look at it from the side, it sort of looks like a pyramid. And the base of the pyramid looks like a triangle. So it's Trigonal Pyramidal. So that is Trigonal Pyramidal if you have 3 atoms and 1 lone pair bonded to your central atom. And last but not least, if you have two atoms and two lone pairs bonded to your central atom, the shape you get is bent. And this often happens with oxygen. So imagine you have two atoms, so there are two atoms bonded to your central pair, and two lone pairs. You have two atoms, two lone pairs, and you get this bent shape. It almost looks like a V. There's a bend there. And so that's the shape you get when these lone pairs and the bonds repel each other, and they get as far as they can. So that's bent. So those are your shapes, and you can predict those shapes based on the combination between atoms and lone pairs around a central atom. And based on these shapes, those molecules will either be able to fit or not be able to fit into a receptor site. Or maybe they will be able to react with each other or not. So, we want to, in order to predict the shapes, we want to see how many atoms and how many lone pairs are around our central atom. And so for each of these molecules, our first step is to draw the molecule. Take this molecular formula and draw it out. And we're going to use those shortcuts that we learned in the beginning of this chapter. So nitrogen, we saw, tends to have 3 bonds and 1 lone pair, because it's in group 5a. So it has 1, 2, 3, 4, 5 valence electrons. You've got that lone pair on the top, and the unpaired electrons can form bonds. So that's nitrogen. And hydrogen is in group 1a. We saw that because it's in 1a, it has that 1 valence electron, so it tends to be able to form just 1 bond. And so to figure out how this molecule fits together, we can take the bonds and make them overlap. So they share that bond. And so this would be the structure for NH3, which is ammonia. And you would see that in like drain cleaner or cleaning products. So if we're interested in this, we are interested in this central atom, the nitrogen. And so we want to ask ourselves how many lone pairs and how many bonds are around that. So, or how many lone pairs and how many atoms are around that. So we have 1, 2, 3 atoms bonded to that central atom. So we have 3 atoms, and we have 1 lone pair. And so when all of those push against each other, we saw that the shape that makes, 3 atoms and 1 lone pair, is trigonal pyramidal. Trigonal pyramidal. It looks like a pyramid with a triangular base. And so the geometry for this would be trigonal pyramidal. Okay, H3O+. Let's draw that out. We saw hydrogen tends to form 1 bond. So we have 3 of those. We have oxygen. Oxygen is in group 6a. And so that means it has 6 valence electrons. So 1, 2, 3, 4, 5, 6. And that means that you would usually be able to form 2 bonds. And so once we have those pieces, we can start to piece them together, make the bonds that are available overlap. I'm going to take this hydrogen, I'll put that bond on the other side of it. That hydrogen bond the bond on that hydrogen can overlap with that one. And then there are no other bonds on the oxygen, so what we're going to have to do is, instead of making a bond overlap, we're going to have to take a lone pair. Oops. And with that, when we take that lone pair, we will make that overlap with the bond. And so that really is just 1 bond there. So we can get rid of those circles, that's the bond. Okay, so that is our structure. Let's look at that central atom. How many atoms are bonded to that? We've got 1, 2, 3. So we have 3 atoms pushing against each other. And we have just 1 lone pair. Remember, there are 2 electrons in a lone pair. So we have 1 lone pair. And so that combination of 3 atoms and 1 lone pair, we saw when all those push against each other, gives us a trigonal pyramidal shape. So this will also be trigonal pyramidal. That, as different as that molecule looks from NH3, the molecule we were talking about in A, nonetheless, they have the same shape because they have the same things pushing against, the same type of things pushing against each other. And so they would fit into similar pockets. How about BH4-? Let's first draw that molecule out. So we have boron. If you look in the periodic table, you'll notice that boron is in group 6A. That'll be that first box under that 6A column. Or I'm sorry, 3A. 3A. The first box under that 3A column. Under that you'll have aluminum, etc. So 3A. And that means that it has 3 valence electrons. So 1, 2, 3, and it can form 3 bonds. We have 4 hydrogens. Each hydrogen we know can form 1 bond because it has 1 valence electron. And where the bonds overlap, where the bonds can overlap, we make them overlap. So this hydrogen will move in there. And this hydrogen, which doesn't have a bond it would connect with on boron, you can just stick it on. That's actually where this negative charge is coming from, because you're bringing extra electrons onto the boron. And if, just for the sake of review, if you were to find the formal charge on the boron, you'd say, okay, it's in group 3A, minus the dots, 0 dots, the lines, 4 lines, so 3 minus 4, that's negative 1. That's where this negative charge is coming from. Okay, but if we are looking just for the shape, we'll pay attention to that central atom, and we'll ask ourselves first, how many atoms is that connected to? It's connected to 1, 2, 3, and 4. So we've got 4 atoms here. And how many lone pairs? There are none. There are no dots around that boron. So 0 lone pairs. And that combination of stuff pushing against each other, we saw earlier, gives you a tetrahedral shape. So if you have 4 atoms, 0 lone pairs, you get that tetrahedral shape. And so this molecule will be tetrahedral. For BCl3, so we said boron is in group 3A, it can form 3 bonds. Chlorine is in group 7A, that means it has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. This unpaired electron can form a bond, so chlorine can only form 1 bond. We only have 3 of them. And so once we have each of those atoms drawn out with their bonds, we can make the bonds line up. And that would be our molecule. Let's look at that central atom. We have that central atom is bonded to 1, 2, 3 atoms. So 3 atoms. And if you're looking around at it, you don't see any dots, so it has 0 lone pairs. And so that combination of stuff, when it pushes against each other, 3 atoms and 0 lone pairs, gives you a shape Trigonal Planar. So this molecule is going to be Trigonal Planar. So that looks kind of like a triangle from one side, and then it's flat if you twist it. It's existing in a plane, so planar. All right, how about BCl4-? So we have boron. We know boron can form 3 bonds. We have chlorine. We saw that chlorine can form just 1. We have 4 chlorines. And so where we can overlap bonds, we overlap them. And then this chlorine here has a bond that doesn't match with anything on boron. So it uses its own electrons to form the bond, and that's it's by adding those electrons that you get the negative charge on this molecule. If you were to find the formal charge on the boron here, you would say, okay, boron is in group 3a minus the dots and the lines around it. There are 0 dots around the boron. There are 4 lines, so 3 minus 4 is -1, and that's where this charge is coming from. It would exist on the boron. But here we're interested in the shape, so I'll clear that out, not because it's not there, but because I want to focus on the shape. So there is still that -1 charge there. But let's look at the central atom and ask ourselves, how many atoms is that bonded to? It's bonded to 1, 2, 3, and 4 atoms. So 4 atoms, how many lone pairs are around it? And if you look at the boron, there are 0 lone pairs around that boron. So if that stuff all pushes against each other, it results, when they get as far as they can, in a shape of tetrahedral. So that molecule will be tetrahedral because it has 4 atoms and 0 lone pairs, all pushing against each other. So this is tetrahedral. How about CCl4? So here we have carbon. We know carbon's in group 4a, so it has 4 valence electrons, can form 4 bonds. Chlorine, we already saw, can form only 1 bond. We have 4 of them. And so once we have each of those individual atoms, we can just make the bonds overlap. And now we want to look at that central atom, so that carbon, and ask ourselves, first, how many atoms is it bonded to? Well, we've got 1, 2, 3, and 4, so we're looking at 4 atoms there. How many lone pairs are around this carbon? Looking around the carbon, we don't see any dots, so there are 0 lone pairs. And that combination of stuff, all pushing against each other, results in the shape of tetrahedral, like we've seen before. 4 atoms, 0 lone pairs, results in tetrahedral shape. So the shape of this molecule will be tetrahedral. And that'll determine whether it fits into a receptor site or not. How about G? So here, we have 1 carbon. We know carbon forms 4 bonds. We have 1 hydrogen. We know hydrogen forms 1 bond. And we have 3 chlorines. And we know that chlorine also forms that 1 bond. So once you have the individual atoms, you can make the bonds line up. Once you have the molecule, take a look at that central atom. You can see that that's bonded to 1, 2, 3, 4 atoms. And there are no dots around the carbon, so you have 0 lone pairs. And as we've seen before, the combination of that stuff, 4 atoms and 0 lone pairs, all pushing against each other, gets them as far apart as each other as possible when the molecule is tetrahedral. So they push each other into a tetrahedral shape. And so this molecule here would be tetrahedral. All right, last but not least, we've got Dichloromethane Ch2cl2. You wouldn't have to know the name for that. So we have 1 carbon. Carbon forms 4 bonds. We have 2 hydrogens. Hydrogen forms 1 bond. We have 2 chlorines. We saw chlorine forms 1 bond. And so we can line up these bonds with each other. Once they're all taken care of and there are no random bonds just pointing out in space, not pointing at anything else, we can look at that central atom, ask ourselves, how many atoms is that carbon bonded to? 1, 2, 3, 4. So that's 4 atoms. And around that carbon, there are 0 lone pairs. There are no dots. And so we see again this very popular shape in organic chemistry, because whenever carbon has 4 single bonds and no lone pairs, it'll take this shape. And that shape is tetrahedral, 4 atoms, 0 lone pairs. So this molecule is going to be tetrahedral. Just because it shows up so much, let's take another look at what tetrahedral looks like. So if you have a central atom and you bond it to 1, 2, 3, 4 atoms, you get this tetrahedral shape. And so that's what those last 3 molecules would look like.